here's a statement that I hope all of you know to be true, and that is that a number divided by itself is equal to 1, provided that that number is not 0. That's also true here. X to the a power divided by itself is also equal to 1, provided that x to the a power is not 0. So now let's apply the rule, the quotient of two powers with equal bases. That gives us that x to the a divided by x to the a is x to the a take away a, because the rule allows us to subtract the exponents. Well, a take away a is 0. Well, all of the exponents we've worked with in previous lessons were positive integers, but now we're looking at 0 as an exponent. And if this is all true, then x to the 0 power is 1. And it is true. The 0 exponent is defined for any non-zero number x to the 0 power is equal to 1. And while that can't be explained using the definition of exponentiation, because notice, the definition of exponentiation applies to only positive integers for a. So let's explain it another way. Let's look at a number that we can work with easily, 2. We know that 2 to the third power is 2 times 2 times 2, which is 8. 2 to the second power, also known as 2 squared, is 4. 2 to the first power we know is 2. Those can all be explained using exponentiation. But now, let's look at a pattern we're seeing developed. 8 divided by 2 is 4. 4 divided by 2 is 2. If we continue the pattern, we should do 2 divided by 2 to get 1. And on the left side of our equations, the pattern would be counting down the exponents, 3, 2, 1, 0. And we can even go a little further. If we divide by 2 again, we get 1 divided by 2, or 1/2. And following our pattern, counting down, the next integer below 0 is -1. So that suggests that 2 to the -1 power is 1/2. And 2 to the -2 power is 1/4, because 1/2 divided by 2 is 1/4. And to complete and get perfect symmetry here, 2 to the -3 power would be 1/4 divided by 2, or 1/8. And all of that is true, because for negative exponents, for any non-zero number x and for any integer n, x to the opposite of n power is equal to 1 over x to the n power. And you may recognize 1 over x to the n as the reciprocal of x to the n, and that's correct. So that now if we look at x over y, a fraction, we know the reciprocal of x over y is y over x. So for fractions, we can write x over y to the opposite of n power is the same as the reciprocal y over x to the n power. And that gives us that for any non-zero number x, x to the -1st power is the reciprocal of x. And that explains why for many calculators, the x to the -1 key is the reciprocal key. And it's also true that x to the opposite of n power is the reciprocal of x to the n power. And so we can add something to our patterns that we had earlier. We can take 2 to the -1st power and write 1 over 2 to the 1st power, and then change that to 1/2. We can take 2 to the -2nd power and write 1 over 2 to the 2nd power, and change that then to 1/4. And finally, 2 to the -3rd power is the same as 1 over 2 to the 3rd power, and change that to 1/8. And now, let's apply our rule, and we'll get a negative exponent. 4 minus 6 is -2. But we know that x to the -2 power is 1 over x to the +2 power. Both of the final two lines might be considered acceptable ways to simplify the original expression, although we often prefer to write it the bottom way with no negative exponents. A number with a negative exponent in the numerator of a fraction may be moved to the denominator if the exponent is changed to its opposite. And a number in the denominator with a negative exponent may be moved to the numerator if the exponent is changed to its opposite. This is all true because of what we know about reciprocals. So now here's an expression written twice, and we're going to do it two different ways. The expression is x to the negative fourth power times y to the third power over x to the sixth power times y to the negative fifth power. Now the first way we're going to do it is to just apply our rule of the quotient of two powers with equal bases. So for the x we have negative 4 take away 6, and for the y we have 3 take away negative 5. Well, subtracting negatives is a bit confusing, but if you know what you're doing, you get x to the negative 10th times y to the 8th. And then a way that's often preferred is to write it without negative exponents. So instead of writing x to the negative 10th, we put that in the denominator and we write y to the 8th over x to the 10th. Now let's move over to the right and do it a different way. Let's apply the rule we just presented, that we can take the negative exponents, the ones in the numerator, make them positive and move them to the denominator. Take the negative exponents from the denominator and move them to the numerator and change them to positive. So now we have y to the third times y to the fifth in the numerator, x to the sixth times x to the fourth in the denominator. We apply the product of two powers with equal bases, which allows us to add the exponents for y in the numerator as well as the exponents for x in the denominator to get y to the 8th over x to the 10th. The same simplified answer we got it the first way we did this one, so we're happy. In this lesson, we looked at the zero exponent for any non-zero number. X to the 0 is equal to 1. And we looked at negative exponents for any non-zero number x, and for any integer n, x to the opposite of n is equal to 1 over x to the n. And if you're wondering, are there other exponents such as 1.5? Could pi be an exponent? How about negative 2.3? Could that be an exponent? Well, yes, it can, but that lesson is for another time. In this and the previous lessons, we've now looked at exponents, which are integers, and I think we're all equipped to handle expressions with integer exponents.